doctoral defense of Ajay Srinivasamurthy.
That's right, yes.
I hope I got that right. As you know, I'll read the title. It is a data-driven Bayesian approach to automatic rhythm analysis of Indian art music. And being examined today, I'm the first to the jury on Pablo, Bello, and Geoffroy, Peeters, and the other members of the committee examining them. And we'll start off with a presentation from Ajay. It'll be around 45 to 60 minutes, and then we'll have time for questions.
Okay, may I start? Okay. Good afternoon and welcome. I'm here to present some of my work as done as a part of this thesis, data-driven Bayesian approach to automatic rhythm analysis of Indian art music. I would like to start by first thanking Dr. Javier Serra, who has been the thesis supervisor and giving me this opportunity to work on this thesis. And in special, I also want to thank Dr. Andre Holzapfel, who is here and has a major role in the thesis, and all my co-authors and collaborators with whom I worked as a part of this thesis. And I want to thank the jury for taking out your time and then to agreeing to review the thesis, and everyone who is here for just being here. This thesis has been conducted within the context of CompMusic project, wherein we are trying to build culture-aware music information research technologies in our multicultural world, while this thesis mainly focuses on rhythm. The motivation for us is automatic rhythm analysis and its applications. As we know, rhythm is a fundamental dimension of music, and analysis of rhythmic structures and patterns would help us to define rhythm similarity measures, which have a multitude of applications, including enriched listening and then meaningful interaction with large collections of music. The scope and objectives of the thesis, let's look at the long title of the thesis, which helps us understand a little more. Let's break it down and then understand it one by one. The core of the thesis is on automatic analysis, description and discovery, mainly to extract information out of music and then not to create music itself. What do we want to analyze? We want to get and analyze rhythmic structures and patterns, in specific metrical structures and percussion patterns. The way we want to do it is to take a culture-aware approach, wherein we work within the CompMusic and its community, bring lots of music knowledge into our methods, and convert musical concepts into engineering formulations. We take data-driven engineering approaches. This is an engineering thesis where the emphasis is mainly on data and methods. The tools we use in the thesis are signal processing and machine learning approaches, and in specific Bayesian machine learning methods, which try to explicitly include music knowledge and generate novel methodologies for analysis and discovery. The core object of analysis in the thesis is an audio music recording, which is a part of a bigger music collection, though we use metadata from other sources in our methods to help this analysis. The music culture of choice here is Indian art music, because it's a well-studied music culture with significant musicological literature. It has a huge audience and it comes with its own unique challenges, which identifying those challenges is a part of the thesis itself. We also want to explore extensions to other music cultures, while I just want to emphasize that this is the first thesis on automatic rhythm analysis for Indian art music. So in addition, we want to emphasize on reproducible and open research as a philosophy. We want to keep the code open source when possible and the data to be easily accessible or open when possible. So we want to ask two primary research questions here, one related to the data, in which we want to see if we can get some insights about the music itself from the data that we have collected, and from the methods, in which we are saying what would be the utility of such culture-aware specialized approaches that we are talking about here. These two are answered eventually. The topics for this presentation would be to start with the music background to understand what's coming up next. And the main contributions, I would talk about three main things. One is data corpora for rhythm analysis and the problems of meter inference and tracking and percussion pattern discovery, and wrap it up with a summary. Let's start with the background, music background. So Carnatic music is one of the Indian art music traditions. The picture shows a concert. You see that on the left, the main percussion instrument is the mridangam, where there is also a lead vocal and other accompaniments. Rhythm in Carnatic music is organized around metrical time cycles called talas, which provide a broad structure for rendition of music. The smallest time unit, so a cycle is shown here, and then the smallest time unit there is called an akshara, which means a syllable actually. And further, these aksharas are grouped into beats and possibly into sections, which can be of non-equal lengths. And the first beat of the cycle is called the sama, which is marked with the X there. So that's the basic introduction to rhythm. In this thesis, we just focus on 4 different talas in which a majority of compositions are performed in the current day music practice. An example, audio example to listen to, this is an example in Rupak Tala, which is a cycle of 3 beats. Let's listen to it. The downbeat is marked with a click and other beats as well. So I'll go through it. That's the downbeat. So that's how this piece goes. So this is a short cycle just of 3 beats. And then if we move on to Hindustani music, which is another Indian art music tradition, so we see that the percussion instrument accompaniment here is the tabla, which is on the left, and there is a lead vocal and then many other instruments which accompany it. Again, the concepts kind of extend here, wherein Hindustani music also has metrical time cycles called the tal, in which the smallest time unit is called a matra, which are grouped together into sections called vibhaks, and then the first beat of the cycle is called a sum, which is marked with an X. An important characteristic in Hindustani music is that the pieces are performed in a wide range of tempo, which means that the pieces can be characterized and then categorized into slow, medium tempo or fast. This is musically done as well, and then these numbers were got by consulting a professional musician, and we use this in our data sets. So again, we focus mainly on 4 different tals, which are often performed in Hindustani music as well. All of them have different structures. Let's listen to an example of a slow cycle here. This is Ek Tal, a cycle of 12 different beats. I can show the downbeat and then let's try if we can track through the progression of this cycle. That's a downbeat. Beat number 2. So which beat are we on? Any ideas? So yeah, we were on beat number 5 and then it goes on for another half a minute or so before the cycle completes. So this is the cycle that we are trying to track here. So some observations from this music that we just heard. To summarize, we saw that some of the phrasal and melodic rhythmic changes were closely tied to the tal. This was more clear in the first example. And the state of the art, there are all of these terminology, these concepts do not extend because there can be beats that can be non-isochronous, non-equal in length. And underlying rhythmic structures, they were not explicit in the surface rhythm at least. And these musical definitions and terminology has to be converted into engineering formulations, which has to be done as well. So moving to a different topic altogether in music background, the other important aspect when it comes to percussion music around the world are syllabic percussion systems, wherein all of these systems use mnemonics for oral transmission of their repertoire using syllables and which are possibly onomatopoeic, which means that these syllables can be used to define and describe percussion patterns in those cultures. It gives us an analogy of being a language for percussion, wherein percussion can be spoken and it can be used to define patterns, and then it's a meaningful representation for us, and it captures the subtleties in articulation, timbre and dynamics. In fact, vocal percussion is an art form which can get quite sophisticated in concerts. When it comes to context of Indian music, in Hindustani music, the strokes of the tabla, the percussion instrument, are called the bol, and then they are used to define the syllables of tabla. There is usually a lot of syllables that are mapped to the same timbre on the tabla, the same stroke. So we use the same idea to group together several syllables into one timbre and then use it for automatic analysis. In fact, the bowls of the tabla are quite important in the sense that they also define the canonical patterns of a tal called teka. Let's listen to one of the tekas of ek tal, the piece that you heard. This is what the tabla was playing at the background, but at a much slower tempo. So, of course, it was being played at a much slower tempo. This is at a much faster tempo. So, in fact, it's important that way that bowls are used. In Carnatic music, we have an equivalent wherein the strokes of the mridangam are used here. They're called solkatu, and then compound strokes. Again, we group them together for analysis, automatic analysis. So, in summary of the music, both the music traditions that we have here are oral traditions and they're improvised, and Tala just gives us a basic skeletal framework on which music is performed. There is no metronome, there is flexible timing, and there's a wide range of tempo in which Hindustani music is performed. The surface rhythm is indicators, they indicate some underlying structures, but it's not explicit, and both of them have well-defined syllabic percussion systems which needs to be exploited, and they both have unmetered music forms, which is beyond the scope of our automatic analysis. So, given this background in music, we can in fact formulate several different automatic rhythm analysis problems in Indian art music, and then in fact link them up based on how they relate to each other. But in this presentation, I'm just going to talk about three of them. One is building data corpora, and then automatic rhythm annotation as exemplified by analyzing metrical structures, and rhythm and percussion pattern analysis. So let's look at each of them one by one. So starting with data corpora for research. Since we are trying to do data-driven research here, we need a research corpus which needs to be representative of the real world which we are operating in. And with this research corpus, we do our research. But then when we want to specifically work on an MIR task, and then we have to build methodologies for that, we build smaller test data sets which can be smaller and then can be used for building that particular task. These test data sets are mostly part of the research corpus, but then of course they can come from real world recordings, not in the corpus, and in fact even synthetic data if there is a need for that. So in fact building these research corpora itself is a research problem, and then a systematic approach to building MIR corpora and an analysis of a specific Indian art music corpora is in the document. What we'll focus on here are test data sets that we have built for different MIR tasks, and we'll be using them in experiments. These test data sets are rhythm related, and then they can be categorized into two parts. One is the rhythm annotated data sets which have information about the tala included in them, while we also have data sets for percussion analysis. So it's important to note that all these annotations are public, and then the audio is commercially available, and hence everybody has access to it if they want to pursue it further. So let's start with the Carnatic music rhythm dataset. This is a dataset with about 16 hours of beat and downbeat annotated music. And then we also created a smaller subset. The bigger subset has mainly full-length pieces, while we created a smaller subset just of 2-minute excerpts, which is about 4 hours of music. And in terms of numbers, both of them have 120,000 annotations, and the other one has about 28,000 annotations. If we look at Hindustani music rhythm dataset, we again built about 150 2-minute excerpts and then annotated them to about 5 hours of music. But given that Hindustani music has this wide variety of tempo, we have to split it up. We split it up into two different subsets. One is the long cycle subset, which just has slower pieces, the ones similar to the ones that we heard, and short cycle subsets, which has all the other pieces much faster in tempo. So in fact, one of the things that we wanted to do with these annotated data sets is to do a corpus level analysis and to understand how the rhythm in this can be characterized. 3 main analyses were done in terms of tempo, range and distribution, analysis of cycle length rhythm patterns, which we will see in the presentation, and also intra-cycle tempo variations as well. All of these are being compiled into an article that's under preparation right now. So why are we interested in cycle length rhythm patterns? Because they are musically relevant, and then they are useful for any analysis of meter. So how do we do it? We use spectral flux feature, which are indicative of onsets. We compute it starting from the audio signal in 2 different frequency bands. The signal flow there is quite standard. And then once we have that, we use the annotated data and then chop out cycle length sequences of features and then put it on top of each other, average them out. and then over the entire data set, and then we have patterns. How do they look? These patterns look like something like this. So this is an analysis for Hindustani music. We want to plot it separately for the long cycle and the short cycle subsets. The bottom panel here represents the left bass strokes of the tabla, low frequency band mainly, and the high frequency band are mainly right strokes of tabla and anything that did not get averaged out when we kind of put it all together. With these two, there are several different observations that can be done from these patterns, but then we'll just look at some very key observations. In the long cycle subset, we see that there are stronger accents on the matra. In fact, the structure of the tala is in fact shown there with X again denoting the downbeat. Here we see that accents are stronger on the matra. Matras are the anchors on which the music is performed, and there are fillers between the matras where that maintain as continuity. In fact, in the example we heard, there were other tabla strokes being played even though it was not on the beat. So those are fillers. In fact, one important observation, there are others. One important thing in Hindustani music is that the main lead musician tries to indicate when the downbeat is coming up. So, and then we see a strong accent on one of the beats which are approaching the sum. This is an important observation. If we kind of look at the short cycle subset, we see less fillers here because the cycles are much shorter. There's no fillers required to keep continuity. And then the vibhaks or sections become anchors here instead of matras because the matras are too short in duration. So that's an overview of what can be observed from here. There are many more things documented in the thesis document. Again, Tintal shows that this a similar observation, it's indicating that the downbeat is coming up. Moving to the percussion data sets, we have tabla solo and mridangam solo data sets. Both of them, in fact, tabla solo has about 17 minutes of audio with time-aligned syllabic transcriptions from 38 different compositions, all of them in Tintal, the cycle of 16 beats. They have syllable annotations with these 18 grouped syllables that we talked about, wherein we grouped them by timbre. The mridangam solo dataset again has about 24 minutes of audio and 8,000 syllables, but the annotations were not time aligned when this thesis was done. But then IIT Madras, which created this dataset, now has time aligned annotations which can be used now as well. In order to evaluate some of our approaches and to establish some baselines, we use the ballroom dataset, which is a popular dataset used in state-of-the-art meter analysis tasks. So we use that as well for analysis. It has 697 30-second clips. Both of them have beat and downbeat annotated in 2 different time signatures. So that was about the data. So if we move to the task of meter inference and tracking, which is the main topic of the thesis, we can start by defining the task at a higher level, wherein we say meter analysis refers to an analysis of different aspects of meter such as beats, downbeats, tempo, rhythm classes, and then rhythmic patterns. So the goal in essence is, given an audio recording, we want to align it with different positions of the cycle, whichever positions we are interested in. This is a cycle of 5 beats, but then sometimes we are not interested in beat number 2 and 5. So they are omitted, but then, so that's the eventual goal. And then, of course, in fact, to infuse a lot of music knowledge into our methods, we have formulated different meter analysis tasks in the context of Indian art music, starting with most uninformed to the most informed. And the first of them is meter inference, the task. This is the most uninformed task, in which just an audio recording is given to us, and then we have to analyze the rhythm class, which is the tala, and the tempo, beats and downbeats, everything from automatically. The other task which forms our baseline is the meter tracking task, in which the rhythm class or metrical structure is already known. This is a fair assumption because it comes from editorial metadata of most recordings, that the tala is already given to us, and then we want to estimate the tempo, beats and downbeats. And we go one step further as informed meter tracking, wherein one of the categories is tempo informed meter tracking, wherein a tight tempo range is given. So we assume that tempo is estimated elsewhere automatically, and then is given to us, and then we can estimate the remaining aspects of meter. And the last, the most informed task is tempo plus downbeat informed meter tracking, wherein the tempo and a few instances of the downbeat both are given to us, and then we want to analyze using this. The last task in fact has a nice practical application, in the sense that We can use this to annotate large music collections with a little bit of manual intervention, wherein a musician or a music listener can tap a few beats and downbeats, and then from that we can get an estimate of tempo and also where the cycle starts, and then use that for tracking. So it can be used in a nice application. In terms of the state of the art in meter analysis, the tasks related, which are tempo estimation, beat tracking, time signature estimation, and downbeat tracking, all of them have been independently addressed as well. But very recently, there have been integrated approaches which kind of try to bring all of these together in one framework, and that is where we'll start our methods from. But in fact, before even starting on our methods, we want to understand how we evaluate these meter analysis tasks. So this assumes that there is a ground truth sequence of beats and downbeats, and then there is an output that's coming from an algorithm, again a sequence of beats and downbeats. And then once we have this, we can equivalently define evaluation measures for beats and downbeats using the information retrieval measures such as precision, recall, and F measure. But of course, meter analysis always suffers from metrical ambiguity, in which a doubling of or halving of tempo can be equally likely. And then we hence compute these measures at the correct metrical level, annotated or allowed metrical levels, which takes care of these tempo errors. And we compute information gain as well, which kind of tries to relate the annotation sequence with the output sequence, and then sees how much they are related through an entropy based measure. And the continuity of beat tracking is also included in the last measure called AMLT. We'll use these measures for evaluation. Before we even started out with our methods, we wanted to do a preliminary check of the existing MIR state of the art in terms of these tasks with respect to Indian art music. And then in fact, so a lot of these algorithms which existed then did not really address Indian art music itself. So we had to in fact adapt the tasks and then adapt the music, the concepts also to match, so that we could do an evaluation on a single ground. But then basically the key takeaway from this paper that we wrote a few years ago with Andre was that the methods have poor and insufficient performance. There is a lack of engineering definitions for the music concepts that we were working with, and there was a need for methods that explicitly use the knowledge of metrical structures in them. So again, we proposed a further approach, which in fact included information about metrical structures, wherein we started out with an onset detection function computed from the spectral flux feature which we saw. And again, we use the peaks of these, which are indicative of some events of rhythm, and then try to extract the aksharas in Carnatic music, the basic tatum pulse, and also the downbeats, and then use those candidates and then link them up using a cost function using dynamic programming based approach. In fact, it was evaluated on Carnatic music dataset mainly. It did quite accurate tempo tracking, but then it did very poor sama tracking. But what's important to note here is that it was an ad hoc approach, which means that it could not be extended directly or it could not be improved very easily. So we had no way of improving it further, we didn't know. So that's where in fact Bayesian models come in which these are models which can formally incorporate metrical structures in them, and then we can improve them in various different ways. We look at how. So Bayesian models, it's not new. It has been used for joint estimation of tempo, beats, and downbeats. The bar pointer model being the state of the art right now. The way they do it is to use bar length rhythm patterns, just like the way the rhythm patterns we saw, which are often learned from data. But then the main limitation as of now is that they are restricted to shorter bar or cycle durations, and they have problems tracking long cycles. So the basic idea of a bar pointer model, in fact, is to say that we have two different variables that track where we are in the cycle and then how fast we are moving through the cycle. There are two variables that are being tracked. Or more formally, a bar pointer model is a dynamic Bayesian network which has an observed feature sequence that's computed from audio and a latent variable sequence which kind of tracks these variables that I was talking about. And then they are all interlinked through a first order Markovian relationship mainly. And it has an observation model, a transition model that links up the latent variables together, and an initial state distribution. So maybe let's look at understand the bar pointer model briefly so that we can know all the extensions much better. The latent variables here, as I said, are two variables which tell us where we are in the cycle and then how fast we are moving through the cycle, mainly the position and the instantaneous tempo. In addition to that, we are tracking rhythm patterns here, so which means that there is a rhythm pattern indicator which chooses one observation model corresponding to the rhythm pattern that's being tracked. The observation model comes from the spectral flux feature in two different frequency bands. So we take for every position in the bar and for every rhythm pattern we compute a GMM. But since not a lot of things change in a very small amount of time, we tie the states within 64th of a note or a half akshara, and then use that and then just generate one observation model for that small duration of time. So if we sonify the feature, this is how it sounds like. So I can stop here. So the downbeats were marked, and then it's just it's an AM on top of a single sinusoid based on the amplitude of the spectral flux feature. So that's the feature that we are using to track these cycles. It had some information, but then not all the information. So the transition model based on some conditional dependence relationships between the latent variables factorizes this way. To understand the cyclic position pointer, in fact, moves through the cycle and at the end of the cycle kind of wraps back. So that's the position is a cyclic variable, and the instantaneous tempo can be changed. We of course allow for tempo changes only by a small bit based on the previous tempo that we have. So this means that a continuity in tempo is maintained. And we also fix the range of tempo which the value the variable can take. And in fact, coming to patterns, in fact the idea here is to capture a diversity of patterns using many different patterns per cycle. In fact, because the patterns are a cycle long, we allow transitions of patterns only at the end of the cycle, assuming time homogeneity in pattern transitions, which means that the transition probabilities between patterns do not change over a music piece. So once we have such a model, the next task for us is to do inference on the model, which in a way tells us to obtain a sequence of latent variables x star 1 to k. K is the number of audio frames in the music piece, and which maximizes the posterior probability p of x given y. So the latent variables given the observed sequence. So once we have that, it can be translated to more familiar instance of summa or the downbeat or the beats or even a tempo track through the piece. So we explore two different inference schemes, Viterbi algorithm and particle filters. To summarize, the variables that we saw, the position and the instantaneous tempo, they can be discretized, and then the entire latent variable space is now discrete, and then we can use the Cartesian product space of that, and then we can formulate that as an hidden Markov model, and then we can use Viterbi algorithm to obtain the most likely state sequence of latent variables. But then of course the way we discretize needs to be very fine, and then that increases the state space to a large extent, which brings us to a lot of scaling issues. One way to get around that is to compute the same posterior probability pointwise as we move through the piece, in which one of the approaches is to use particle filters, which aim to estimate and approximate the same posterior probability using a set of points in the state space and then assigning weights to them. These are called particles. A particle filter in this case would sample the latent variable at any frame and then compute a weight associated with that and then move forward through the whole music piece. There is a long derivation of particle filters and how do we choose them and then how do we build them. But then to summarize, we use the auxiliary mixture particle filter, which is a particle filter algorithm, which can in fact track multiple hypotheses over time and then choose one at the end, which is necessary for us when we have a lot of metrical ambiguity in tracking meter. So this was the state of the art bar pointer model. What's novel in the thesis is that we extended it and evaluated it on Indian art music datasets, and then we also evaluated it for multiple rhythm patterns per cycle, which was not done before. And we have proposed novel extensions both by changing the model characteristics and also changing the way inference is done. Let's look at these extensions one by one. So the first extension we want to talk about is a mixture observation model, wherein the basic idea here is we want to capture the diversity of patterns that occur in music, but then we also want to do faster meter tracking. So in fact what we can do is, one way to simplify the model is to take off a few of those links, which makes it more independent and then makes the inference faster. But then at the same time, we want to retain some diversity in patterns. So the way we compute the observation likelihood is to average over all the patterns. So that's the basic idea, which was presented in ISMIR last year. The other extension which we wanted to explore was, in fact, it's motivated from the way people listen to music. So if we listen to that Vilambit slow piece, a lot of people who, when they're listening, they are not trying to track the whole cycle, keeping the entire cycle in mind, but only shorter sections of that, which are also musically defined. And then they use that smaller patterns to track the whole cycle. And then the idea was here in the same, wherein instead of using cycle length patterns, what happens when we just use section length patterns and then use that for tracking. In fact, if you see the section pointer model is a generalization of the bar pointer model, wherein in this case we are saying if the section is bar length, then it becomes a bar pointer model. So it's a generalization that way. So this was presented in ICASP this year. In terms of inference extensions to the bar pointer model, so one idea we had was that so when we are trying to track a pattern, we don't know which pattern has occurred in this particular cycle until the end of the cycle. So once the end of the cycle comes, we can look at all these observations and then say, okay, fine, this is the pattern that occurred here. But then most of the inference algorithms sample this pattern at the beginning of the cycle then fix it for the current cycle, which is suboptimal. And then so one idea was to defer the decision of sampling this rhythm pattern to the end of the cycle. And we can also do faster inference by doing inference not at every audio frame, but then only at certain places which we think are more interesting. So one is peak hop inference, wherein we only do inference at the peaks of the spectral flux function that is giving us the feature. And onset gated weight update, which the idea is similar, wherein we want to maintain continuity in inference, wherein we do inference at every place, but we update the weights of the particle filter only at those onsets or onset peaks. So that was the inference extensions. So to summarize all these models, we started out with the state-of-the-art bar pointer model, and then we proposed two model extensions, mixture observation model and section pointer model, and three different inference extensions. So if we want to evaluate these models, the basic idea of experiments here is to look at the tasks of meter inference, meter tracking, and informed meter tracking for both Carnatic and Hindustani music mainly, and compare performance across models for in these Indian music datasets, and to identify any limitations and challenges. The setup of experiments, we assume that the music culture is known, so all experiments are separately done on each dataset, and the results we report it only on the smaller Carnatic music dataset and the two subsets of Hindustani music. So in essence, for Hindustani music, the analysis is also tempo class informed or lie informed. So it knows if it's tracking a fast piece or a slow piece. And the measures we use are the standard measures of F measure, information gain, and AMLT for beats, and just F measure for downbeats with a 70 millisecond error margin, except in the case of when we are tracking longer cycles, wherein we use a little more liberal evaluation criteria of 6.25% of median inter-annotation interval. This is a problem which is more or less, it's still a problem that we have to still work on and then explore further to see how do we evaluate such long cycles. So, but then that's what we use in this thesis at least. For estimation of tempo, we use 5% margin to say if it's correct or not. The results are reported only for single pattern per cycle case, while we comment on multiple patterns later on. The average performance over all pieces over three different trials are reported. The tempo range is fixed a priori based on the idea we have of the tempo ranges, and the mixture particle filter uses 1500 particles per rhythm pattern. So that's the setup. If you look at the tables, the tables have a lot of information. I'll just summarize some key insights from that very qualitatively. And then we can come back if there is some discussion. So all these tables show the music culture or the data set on the left, followed by the beat F measure, beat AMLT, information gain, and downbeat F measure on these columns here. And if we jump into some results for meter inference, so we saw meter inference also does a subtask of Thala classification, which says we want to say which rhythm class a piece belongs to, and then we see that that's better on short duration cycles, and it's very poor on long duration cycles. And in general, the performance is poorer on the long cycle subset of Hindustani music, and we see that ballroom dataset in fact does much better than Indian music datasets for this task. So we were, and then in general we also noticed that summa tracking or downbeat tracking is poorer than beat tracking. We also want to set up another baseline in terms of meter tracking with the bar pointer model, which is our baseline. In fact, it just showed that the performance is better when we already know the rhythm class. So there is an improvement from meter inference already here. And HMM, the Viterbi algorithm and the particle filter algorithms, they provide us similar equivalent performance. So we'll use the mixture particle filter for all our experiments in the future. With the mixture observation model, since we are reporting results with just one pattern, it's equivalent to the bar pointer model, the basic particle filter, and then the performance also is equivalent. But then when we look at the section pointer model, the section pointer model is not evaluated on the ballroom dataset because we don't really have musically well-defined sections in that. So we report only on Indian music datasets. And the basic key takeaway here is that so the summa tracking or downbeat tracking improves with the section pointer model. Beat tracking also improves, but then to a lower extent. In terms of inference extensions, though all of them were they were faster and then they were better doing inference, but then they did not provide any significant improvement over the baseline. And the main tasks of informed meter tracking, tempo informed meter tracking, and then eventually tempo summa informed meter tracking, both of them produced incremental improvements, mainly in tracking downbeats, and then we see that as we give more information to the system, it does better. A big summary of all the results, the first column here shows the different tasks of inference tracking, tempo tracking, and tempo informed and tempo summa informed. And the basic thing to observe here is that there is a gradual improvement in performance as we go through different models, as we build better models, and as we bring in more information, there is a gradual improvement. In fact, we start at about 0.4 F measure and then reach about 0.8 F measure for informed tracking. So that's the key summary of results here. Some observations which are not in the table so far. We also tested out these approaches on full-length pieces of Carnatic music in the big dataset that we saw, and the results extend. So which means that the algorithms can be used for full pieces as well. Of course, there is a computational in terms of there is a problem with computational power, but then that's something that can be solved. The Vilambit pieces are still difficult to track. So despite all these models, the slow pieces are still very difficult to track. In fact, that brings us back to some fundamental questions in terms of how do we evaluate or how do we even formulate the task of meter analysis in terms of those long cycles. It's a question that we have to continually probably work a little more and then understand it more. We tried out with multiple patterns per cycle, but then that did not provide us any significant improvement. The hypothesis for that is that we need better features. The spectral flux feature that we saw is too simplistic to make use of all the patterns coming together and then producing any improvement there. The inference extensions as well did not give us any additional improvement. The most promising, of course, is the section pointer model, which is a generalization of all the state-of-the-art models that we have right now. And then we need to evaluate this further and then understand its characteristics more, and then we can probably use it in a larger scale with different music cultures and then extend it further. So to summarize, these Bayesian models, they explicitly considered metrical structures in their formulation, and they are quite flexible, and then they can be generalized to similar structures across other music cultures as long as we have some training data to train the initial models. The Bayesian models can also be additionally used to impose additional structures on top of this, like such as tighter tempo or allow for human errors when somebody misses a beat. So these are all possible with the Bayesian model framework to be done. And then these models, the ones that we have evaluated at least, assume that the tala does not change, which is mostly true in Carnatic music, but then in long Hindustani music concerts, tala can change in the middle of the piece. So that needs to be handled in some way. And the last one is to use more richer representations of audio, and then using probably also including melody based features, which also help us in tracking progressions through cycles, and then using these models with those features and then see how things improve with that. So the last task for today is percussion pattern discovery. So far we have been talking about rhythm patterns, and the percussion pattern is is a pattern that's played in a percussion solo by a percussion instrument. The task of percussion pattern discovery itself is to search for these percussion patterns from large audio recordings, and the approach we take is a transcription followed by search, wherein given an audio recording, we want to transcribe it to an intermediate representation and then use this representation to search for patterns. So, but as soon as we come into the context of Indian art music, the intermediate representation is using the syllables of percussion itself, wherein we can use the constituent syllables to define percussion patterns, which gives us a more sparser but a richer representation in terms of information. For this thesis, we define patterns, percussion patterns, to be just sequences of syllables without considering dynamics or timing, which is a very simplistic definition, but then it's good for an exploratory study. So the transcription in this case means audio recording to a sequence of syllables. So this task in fact was explored both on Beijing opera and Indian art music. We'll just look at some results from Indian art music here. The task for Indian art music consists of 3 different steps, wherein we first use a score corpus, a corpus of music scores, and then we build a library of query patterns which are characteristic, which are also short syllable sequences, and then given a new recording, we want to transcribe it into a sequence of syllables and then use the query patterns and then search for them in the automatically transcribed sequence. Of course, transcription has errors, so we need an approximate search for these patterns. If we go through each step in detail, this is a block diagram of a system we proposed for percussion pattern discovery in tabla solos in last ISMIR. So there are different components again. First is to build a pattern library, wherein to start with, we said that the most occurring patterns in the score corpus are the most characteristic. This is one of the definitions, but then it would work with any other definition as well. But then we also had to do a little bit of manual intervention to select a set of musically representative patterns from the ones that were extracted. They are of different lengths, and then you can see it for both tabla and for mridangam solo performances. So once we have these patterns, so we want to do automatic transcription. Here we take the analogy of speech again, and then we say that the task of transcription is similar to a limited vocabulary continuous speech recognition with word models, wherein the words are equivalent to syllables and then a sentence is a pattern. So we build models for words, mainly hidden Markov models for each syllable, and then use a simple language model when we are trying to decode a new audio recording. So in a little more detail, we start with audio and transcriptions for training, and then we extract MFCC based features and initialize hidden Markov models for each syllable, and then eventually train them into and then obtain 7-state left to right hidden Markov models for each syllable. And then given a new audio recording, we extract the same features and then use it for beta-B decoding along with a flat or a bigram language model. A flat language model assumes that there is no relationship between syllable transitions, whereas a bigram associates probabilities for transition of syllables in the sequence. So of course, transcription, as we said, has a lot of errors, mainly in terms of substitutions, insertions and deletions, which means that we need approximate search methods. In this thesis, we use an approximate search method which is called the rough longest common subsequence method, which it's known to be robust to transcription errors, and then it can also track multiple occurrences of a pattern within a longer composition. Of course, like most string search methods, this is also dynamic programming based, which assigns cost functions to rough matches in the query and a target sequence of syllables, and then it uses a similarity function between syllables to compute how far they are or how close they are based on timbre, and then it obtains a cost function which we can threshold, and then we can say where a particular pattern occurred. There are many variants of RLCS which kind of play around with the cost functions and similarity measures there, but then we'll report only results for a binary syllable distance measure, which says that 2 syllables are the same and they have a zero distance if they are the same, and then a non-zero distance if they are not the same. The experiments were conducted both on mridangam and tabla datasets, while since we didn't have time-aligned transcriptions for the mridangam dataset, we could not initialize the HMMs for that more accurately. To evaluate transcription, we use two measures. One of them is a stricter measure, which includes insertion errors, and a more lenient measure of correctness, which does not include insertion errors. These two measures are used in speech recognition as well. Approximate search, to evaluate them, we use precision recall and F measure, which are information retrieval measures, and we assume a 70% overlap of the pattern with the query to be correct, and then we don't do any accurate boundary estimation in this task. So some qualitative results. So we see that for the Tabla dataset, we saw that a bigram language model which uses syllable relationships to perform better in test conditions, and then that's the output we use for approximate search. For approximate search, we use the query patterns that we generated, and then we established the baseline, which essentially says we can directly search for these query exactly through the output sequence, and then that gave us an F measure of 0.3 approximately. And of course, when we used RLCS, the performance improved a little bit, the recall improved a lot, and then but precision came down because of false positives, because RLCS can handle rough matches as well, and F measure also improved to a little extent. And the different variants of RLCS that we tested, they did not provide any improvement, which needs, I think, much more experimentation. To summarize, on Tabla dataset, the best transcription performance was from a bigram language model, and RLCS improves over the baseline, whereas the variants did not add much value. So if we listen to an example which was retrieved, so this is the composition we start with. So this one is one of the easy compositions in the dataset. While this was one of the patterns that was retrieved, it's Dhagetata. Whereas this also was the same pattern, but then if you listen to it, it has two extra syllables at the end. So it's not the most optimal retrieved pattern here. So if we move on to the Mridangam dataset results, we see that on average, the performance on the Mridangam dataset is already much better than what we saw for Tabla. But the best result was on a flat language model, which did not assume any relationship between syllable sequences. And in general, if we also saw the baseline, which was the exact string search, was already quite high. And then the best performing RLCS, which gave us the best F measure, in fact, matched up to the baseline. And also, if we looked at, and then if you change the parameters to get the best recall, then the precision drops quite significantly, and then the F measure also drops. In fact, we went about seeing why this happens, and then I think both of them can be attributed to the way data is in the Mridangam dataset. The Mridangam dataset, unlike the Tabla dataset, which are full compositions, so if I played the whole composition there, it would go on for about 40-50 seconds, whereas the Mridangam dataset already had segmented phrases, which meant that the query patterns that we are using and the patterns that were present in the compositions, they were of the same length. And then in that kind of a case, RLCS did not add much value. It's trying to search for a short pattern in a short target pattern again, and then RLCS did not add value there. And then language models did not help either, because when we have shorter patterns, it's difficult to learn very good, so to say, sequence characteristics from short patterns. So that's what we think happened here. So in just to summarize the task of percussion pattern discovery, most of these experiments in pattern analysis were mainly preliminary, and it needs further exploration with more data added both to the Tabla and Mridangam datasets. And what's more important is we need a comprehensive pattern definition, which also includes dynamics and timing, which also is quite important. And we want to improve the pattern boundaries by using onset detection or a method which is similar to that. And of course, we need better RLCS, which can take care of better similarity measures between the timbres, so that we get temporally similar patterns as being retrieved. So that was this task. So to summarize the entire thesis, so I'll just start by briefly describing two applications, very briefly, which include some of the work from the thesis. The first one is Dunya, which is a collection of data and tools which have been developed in CompMusic. It has some components from rhythm analysis here. And also Saraga, which is an application for enriched music listening, which brings together a lot of metadata of music and then puts it together so that we can listen to it in both Hindustani and Carnatic music. I think Sankalp would talk a little more about this. So if we look at the contributions, creating a large data corpora was one of the important contributions in the thesis. Apart from the data corpora we already saw a little while ago, two main important things I want to mention here are the Creative Commons music collections, which are about 40 hours in each of Carnatic and Hindustani music. Each recording here has some annotations, downbeat annotations. So it's a large collection which can be used for practical applications of rhythm analysis as well. And in percussion datasets, we can mention about the percussion pattern and percussion instrument datasets for Beijing opera, which is also present if somebody wants to pursue research in that. The technical and scientific contributions at a broad level, we identified challenges, opportunities, and also relevant automatic rhythm analysis research problems in Indian art music. We gave an engineering formulation for meter analysis and percussion pattern discovery in Indian art music, and there was an illustrative evaluation of the data sets and the research corpora of Carnatic and Hindustani music, and a rhythm analysis of the rhythm annotated data sets itself of both Carnatic and Hindustani music. But the main contributions were to build Bayesian models for meter analysis in Indian art music, and also propose novel extensions to the existing bar pointer model. Finally, some preliminary experiments with percussion pattern discovery from percussion solos, utilizing the syllabic percussion systems that are underlying it, and also suggesting a timbre mapping which can be used for automatic analysis with much lesser training data. So these were the publications which came out during the period of thesis. So some more, and then there are two more articles which are under preparation right now. The additional resources from the thesis are on this page, which and in fact lists down some more examples if we want to listen to it, and then there are also videos which explains progressions through the talas. And the data sets are described in a little more detail on that page there, and there is some code for some parts of the thesis. And then there are results in terms of audio examples which we can listen to and then understand how meter analysis is working on different examples. If you go to that page, you would see a list of methods and then the outputs from each of those methods. And then for both Carnatic music and Hindustani music for different talas, maybe we can listen to a few examples there. And there are some retrieved patterns. In fact, the patterns that I played a while ago are from this page, which can also be used. This is mainly for tabla. From a personal point of view and in terms of thesis impact, this had a lot of broad topics. The thesis addressed a lot of broad topics, and then since it was the first thesis in rhythm analysis for Indian art music, some of the experiments were exploratory, but then we opened up a lot of research problems in rhythm and Indian art music together, and also created data sets for data-driven research in those problems. And then in terms of a personal experience, the biggest impact for me was this coming together of multiple collaborators with very different diverse skill sets, and then all of them coming together and an opportunity for me to work with them and then learn from them. That has been the most enriching experience for me. So there are of course many open ends that are in the thesis. We just barely scratched the surface of meter analysis and pattern discovery, and but then the main tasks of rhythm similarity and structural analysis, which can build on top of these two building blocks, was still not addressed, and then it remains to be seen how we can analyze large amounts of music data, also bringing a lot of domain knowledge, and then combining all these approaches together into a place where all of them can be interlinked and then they can be studied together. So this is the companion page again. Thank you very much for your time.